We're going to explore how gradient descent works with our optimal solution using a 1D example. So in this example, we have that rdy and ry are scalars, and so is w. So writing this out, we have wi plus 1 is equal to wi plus mu rdy minus mu ry wi. We'll combine those wi terms to give us wi plus 1 is equal to 1 minus mu ry times wi plus mu rdy. Now this looks a lot like a linear filter, a recursive filter that we may have seen in other DSP classes. So in this example, our mu rdy acts like an input. It's actually a constant input. Our wi looks like our previous output, and wi plus 1 would be our current output in our recursive system. And the recursive gain parameter here is r1 minus mu ry. So we can draw this now as a linear system that, such as we might have seen in in a DSP class. Here we have a recursive filter. The z-transform is given by 1 minus our recursive gain coefficient, z minus 1 on the bottom there, constant input, and the output is our updated filter weight. So this only converges if 1 minus mu ry is less than 1 in magnitude. This is only the case when mu is between 0 and 2 over ry. We're assuming here that ry is positive because ry is going to be a autocorrelation value, and so this all works out. So we can now pick mu so this converges. The question is, what does it converge to? Well, we know that at w is equal to infinity, or I is equal to infinity, w infinity is going to be a fixed point if it's converged. So if this is the case, then the w on the left and the w that's multiplied by the 1 on the right are going to cancel, leaving us with just mu ry w infinity is equal to mu rdy. And obviously we can cancel out these mu's because they're positive numbers, giving us our Wiener solution that we came up with on the previous page. So this is exactly what we want. It converges to the Wiener solution in this 1D example. Now let's explore how fast it gets there. We obviously don't want to wait for infinity. We would like it to hit the optimal solution sooner, and the question is, how soon is it going to hit? To answer this question is a little bit more tricky than just following the filter dynamics, although we'll find that it's pretty similar. The reason why is that although we use that linear filter example up above, we do not have 0 initial conditions. In general, we're going to pick w0 to be maybe our best guess, or maybe a random guess, but it's not necessarily going to be 0. So we're going to take a page from this previous analysis, and we're going to note that the optimal solution is that converged fixed point, and this will help us describe the dynamics of the equation in a little bit different or easier way. Next, we're going to note that w1 is going to be simply our initial guess or our initial condition after a single update. Now we can use this to plug into that equation and express the whole thing in terms of misadjustment, which does behave in a very easily described manner. Now we can gather terms, and we get, actually before we do, let's define Wi, delta Wi as Wi minus W opt. So this is our misadjustment at time I. Using that new definition and combining terms gives us that the misadjustment at time 1 is equal to 1 minus mu Ry times the misadjustment at time 0. You can verify for yourself, or you can take my word for it, that if we were to continue this, we are going to find that the general relationship is Wi is equal to 1 minus mu Ry misadjustment at time I minus 1, and if we just follow that all the way through back, that's going to be now we have this power function of 1 minus mu Ry. So from here we can see that the smaller that 1 minus mu Ry is, the faster our misadjustment is going to decrease, or the faster we are going to converge to the optimal solution. With that in mind, we can pick the optimal value for mu, and that would be that mu equals 1 over Ry gives us convergence in a single step. This shouldn't come as too much of a surprise, because if we can invert Ry, which in the one-dimensional case is just 1 over Ry, then we can come up with the optimal solution right away. So once again, if we can invert Ry, even in our gradient descent, we can come to the optimal solution very, very quickly. In general, though, we don't want to do that. One dimension might be hard, many dimensions is more difficult, but that gives us some idea. Also note that if 1 minus mu Ry was a very small negative number, it's still going to converge just as fast as if it was the same very small number but positive. So either one is okay. It just needs to be close to 0.